Okay, this is a pretty fun exercise to do with the real hardware, or at least to watch a video of with the real hardware. This is part 3 of lab 20, our Mosfet lab. And uh, we're going to illustrate, this is basically a Mosfet switch. Okay, so we're using this Mosfet as a switch. You make VGS big, like much higher than V threshold, or higher than V threshold, then the MOSFET turns on and current flows from drain to source, thereby turning on the lamp. There's drain, gate, source. And then you pull the gate down below V threshold, and the MOSFET turns off, and the lamp goes out. And what's amazing is just how teeny, I mean, there's really no current. The negligibility of the current needed to turn this transistor, this MOSFET, on and off, because the gate current, remember the gate is separated from the channel by a layer of insulator, so there's really absolutely negligible DC current. And to illustrate just how absolutely negligible that is, so first let me show you what I wired up here. So going from left to right, we have gate, drain, source. So going into the gate is this 10K resistor. And then at the drain, I have this black wire going up to the light bulb, going up to plus 5 volts. So I'm using the VCC output of the EE board instead of using VP plus, because VCC is either 3.3 volts or 5 volts. So that guarantees that I don't accidentally use 9 volts and burn out the light bulb, since I only have one light bulb in my kit. So I'm trying to take extra precautions so that I don't burn out the light bulb. And I even left VP plus and VP minus off. Here, let me show you that. So if I go over to supplies, then I have VCC on, and it's at 5 volts, and VP plus and VP minus are off. That way, there's no way I can accidentally do plus or minus 9 volts. Okay, so that was the drain. And then at the source, I have this black wire down to ground. So what's kind of neat about this, well, first of all, I'll take the black wire. This is going to ground. This red wire is going to VCC, which is 5 volts. So if I touch this here, fine, the light bulb goes off. If I touch this here, fine, the light bulb goes on. I don't even need to leave it touching. I can just touch it momentarily and then let go. And of course, you know, electrodes of some size separated by some distance have some finite capacitance, so a little bit of charge can be stored there. I mean, okay, so you expected me to have to leave this connection here, but I don't have to leave it. I can just touch it instantaneously and release it. And the little bit of charge I move back and forth from the capacitance on these electrodes is enough to bring the gate up above or down below threshold. And that actually is an important fact about using CMOS devices. Later we'll use CMOS logic devices. And a MOSFET has such an enormously large input resistance that this tiny little capacitance at a MOSFET input is enough to hold enough charge. And then huge input resistance means whatever charge you put there won't be drained away. So you can, just by momentarily touching a CMOS input, or even by not touching it, maybe it just powers up that way. An unconnected CMOS input can be just a little above or just a little below threshold. So you get all kinds of mysterious effects from disconnected CMOS inputs because they don't necessarily behave in a consistent way. They depend on the history of what touched them recently to leave a little bit of charge on the gate. So, that's kind of one lesson you take away from this. But here, this is even more amazing. I'm going to touch this 10K resistor right here with my right hand. And then with my left hand, I'm going to touch either 5 volts or ground. Okay, so I'm not going to touch these wires together directly. I'm going to put my right hand here, and I'll put my left hand either here or here. And so whatever charge moves around has to flow through my body. And you'll see that even doing that, I am still able, here, so here, can you see, yeah, well, let me try to make it, okay. So here I'm touching the end of the 10K resistor with my right thumb and forefinger. And you can see the light bulb is off. And if I touch the black wire, the light bulb is still off. Now I touch with my left hand the red wire, the light bulb turns on. I touch with my left hand the black wire, the light bulb turns off. Red wire on, black wire off, on, off, on, off, on, off. So it's really my body completing the circuit at the gate. So that's how minuscule the amount of charge is it has to flow to go above and below. I guess we could probably make some estimate. I guess the question is how far above or below threshold do we have to move it for it to turn on versus off? I guess that's one number we would have to estimate. I guess if you say it's on the order of a volt, and we saw that the gate capacitance was on the order of a nanofarad. So I guess you could say, well, how much charge is that? I guess if you say a nanofarad times a volt, that's like a nanocoulomb. So I guess somehow I have to move a nanocoulomb back and forth. It's kind of remarkable to see this. So if you have time to try this, this is worth trying. Okay, so that was the that's part 3.1, the gigantic input impedance of the MOSFET. And okay, I'm going to move on to the next. I'm going to pause and set up the next part. Okay, here's part 3.2. So we're going to use this N-channel MOSFET to switch a current on and off. And we're going to see what happens versus frequency. And a little foreshadowing, we saw earlier that there's a gate capacitance. So we're going to see that that capacitance at some point matters. And okay. So we have a square wave going between 0 and 5 volts going into the gate through this 10K resistor. Yeah, so I think the thing is there's a capacitance that we have to charge or discharge to get this thing to turn on and off. And I guess we'll see, of course, to get it to turn on and off, it takes some time to move that charge. And we're moving it through this resistor. So I guess maybe we can imagine that if this resistor is too big, then it takes too much time to move that necessary charge from here to here to turn the switch on and off. Now we had a light bulb here before, but we want something we can watch and a kind of predictable resistance. So 50 ohms up here. So 50 ohms, and it's about 5 volts, so that should be like 1/10 of an amp. And if you do V squared over R, so I think these are 1/4 watt resistors. So if we use two 100 ohm resistors, then we're only dissipating 1/4 watt in each resistor, which is okay. So we have two of these resistors in parallel instead of a single 50 ohm resistor, which then would exceed the power rating of the resistor. You'd need a half watt resistor instead of 1/4 watt resistors for that. Okay, so I have here, here is my function generator. So now I'm driving the gate I'm driving this resistor in front of the gate with my function generator, which is going back and forth between 0 volts and 5 volts. And I'm watching my input signal here with scope channel 1. And then I'm watching the drain with scope channel 2. So when the MOSFET is on, this should be close to 0. When the MOSFET is off, this should be 5 volts. So we'll see that go back and forth. And so let's take a look. Okay, so here's scope channel 1. Here's the waveform generator. So they're both going in here. Here's this 10K resistor going over to the gate. Here's the drain. I wanted you to see what's going on. So I ran this little blue jumper over from the drain to this column. And then I have my two resistors, 100 ohm each, in parallel going up to VCC. And I wired VCC up to this blue stripe up above. So this is my 5 volt VCC up here. And then I have the source connected to ground with this black wire. So then let's take a look at the waveforms. Okay, so it seems not too surprising. So yellow is channel 1, is my nice square looking, and maybe I'll change the time scale. So we can go to, I don't know, 200 microseconds per division. So this is my, this is a 1, I think this is, yeah, this is 1 kilohertz. Yeah, so this is 1 kilohertz. And you can see that when the gate is high, the MOSFET is on, so then the drain is close to 0. And you can see that the voltage drop across the MOSFET is tiny, right from drain to source. So the drain gets down very close to 0. And then the gate goes down. Well, maybe not the gate, but the resistor that's driving the gate goes down. And it takes a little while for there's a little delay before the MOSFET goes back on. And I guess we can see what's happening. So yeah, I'm going to use scope channel 3 to look directly at the gate. So let me do that, which I had neglected to do until now. So I'm going to turn on scope channel 3. Yeah, so that's kind of cool. So then you can see, maybe, well, I could offset this, make it a little bigger, but maybe it's okay. Yeah, maybe I'll offset these and make them a little bigger so you can see them better. Okay, so I've switched from 2 volts per division to 1 volt per division, and I've added a minus 2 volt offset. So here's 0 volts, and here's 5 volts. And okay, so you can see that, let's go from off to on. So the yellow trace here, we go from off to on. That's at the resistor, and then at the other, that's over here at the left side of the resistor. Then at the right side of the resistor at the base, we can look at channel 3 in magenta, and we see it kind of shoots up, and then it plateaus for a little bit, and then it goes up more slowly. And my hand-waving explanation for what's happening here, so this is a known phenomenon. It's called the MOSFET gate plateau effect. Okay, so gate plateau. And I think you can look that up. But my hand-waving explanation of what's happening is that the channel is forming as the MOSFET gets close to turning on. So it's pulling a bunch of, let's see, it's pulling a bunch of negative charge. It's pulling a bunch of electrons toward where the channel forms, which is over just near the gate on the opposite side of the oxide layer from the gate. And so then that layer of electrons then serves as an electrode, which is like a bigger capacitance. So I think, see, you're pumping charge into the gate through that resistor, and you're doing it pretty quickly here. I guess it's a small capacitance. And then you're continuing to pump charge into the gate, but the voltage isn't changing. So it seems like that's because the capacitance is rapidly growing. And then now the channel has formed, and you have a bigger capacitance. And so now you get this kind of RC-like curve because you're slowly charging up that bigger capacitance. And I think that makes sense because you've pulled a bunch of electrons closer to the gate, and then the relevant electrode dominating the gate capacitance is closer by, so that's a bigger capacitance. And so I think that's why this charging rate is slower than this charging rate. Also, there's just the fact that as you charge up a capacitor more, the current through the resistor gets smaller. Yeah, so anyway, so I think you can actually read a less hand-waving description of the gate plateau effect in a Mosfet. But I think this little blip here is this kind of neat place where you're pulling the charge carriers in to form the channel. So anyway, so we see that it takes some finite amount of time to go from off to on. Actually, you can kind of see that this little plateau region corresponds to where we're going from off to on, because you can kind of see that in the behavior of the drain current. Okay, now let's try to do the same thing at higher frequency. So this is a kilohertz. Let's go to 10 kilohertz. And then we need to zoom in a little on the time axis. Uh-oh. Uh-oh. Here we go. So we can zoom in on the time axis, and we see that, okay, here we try to turn it off with the yellow curve, we try to turn it on with the yellow curve, and it takes some time to turn off and on. So you see with the magenta curve what's happening at the gate, and it seems like when we turn on, we never quite get all the way on. The gate plateau never quite finishes. And then we turn off, and we don't even get quite all the way off. And I guess you can see the, okay, so here we actually are all the way off, I guess, because the blue curve is at 5 volts. But down here, we never get down to the drain voltage being close to 0, corresponding to the channel being fully conducting. So it seems like putting charge onto the gate is happening too slowly. So we could make that happen faster by making this resistor smaller. So let's try 100 ohms instead of 10 kilo ohms. Let me put that in. Okay, so this resistor was 10k ohms, but now it is 100 ohms. So you should expect charge to flow across it much more quickly. So then let's take a look at the effect on the waveforms. Oh, look at that. So everything is sharpened up quite a bit. So it's the same 10 kilohertz frequency. And I guess we could zoom in on the time axis. So let's look. Okay, so you can see with that resistance, it seems to take, oh, I don't know, like half a microsecond for the channel to form. This little flat region, or the gate plateau anyway, lasts about half a microsecond. So then I suppose we could go up to higher frequency. So here we are 10 kilohertz. Let's go up to 100 kilohertz. And that's still doing pretty well at 100 kilohertz. But I guess you could imagine if we went too much higher, it would start to have trouble. So we could try, well, here's 200 kilohertz. I think it'll still be fine. Yep. Okay, and then we can zoom in a little on the time axis. Okay, and then if we go up to 500 kilohertz. Then remember we were saying it took about half a microsecond for the channel to form. So now it's not quite going all, I mean, it's getting pretty, yeah, it's going just barely going all the way from on to off and on to off. So it seems like this is about as fast as we can really switch with that gate resistance. So that resistance, it sort of takes a little while to flow charge across the resistor into the gate. And I guess, you know, I think we could try to estimate some kind of effective capacitance. The question is, where do we measure the time constant exactly? But, well, let's just say that the time constant is on the order of half a microsecond here. I'm just making this up as I go. But I mean, that is kind of the relevant time constant because it's sort of the width of this plateau and it's roughly the time it takes it to turn on or turn off. So let's say that we have some RC which is on the order of a half microsecond. And then we know that R is 100 ohms. So what is the order of magnitude of the capacitance then? So it seems like it must be 0.5 microseconds divided by 100 ohms. Yeah, which is 0.5 okay, so this is 500 nanoseconds. Yeah, so it's like 5 nanofarads. Yeah. And okay, that's kind of similar order of magnitude to what we saw before. Remember earlier in part 1, we saw a gate capacitance on the order of 1 nanofarad. And I even think it makes sense that we see a bigger capacitance now because I think earlier, well, I have to think if I'm making sense. But I think we saw this capacitance effectively increase as the channel was formed. So maybe it makes sense that we see a slightly bigger capacitance than that on the order of 1 nanofarad we saw much earlier in part 1. Okay. Yeah, I'm not sure I believe my argument about the capacitance making sense to be bigger than it was in part 1. Because I think in part 1 we were looking at the capacitance, the observed gate capacitance when the FET was on. So yeah, so I guess I'm not sure I believe my argument that this should be bigger than it was in part 1. But anyway, it seems like it's the same order of magnitude. If you can offer a good explanation of this, let me know. But to my mind, it's kind of good enough because it says, okay, we see a gate capacitance on the order of a nanofarad, and then you can look up this gate plateau effect. Okay, so part 3.3 is really fun. We're comparing a Mosfet switch to a bipolar transistor switch, but it's not feasible. There's really no way you can do it with your at-home kit because we need these great big power resistors. And so if you try to do it with like these half-watt or quarter-watt resistors, they'll go up in smoke. So that's not, yeah. So, but we do have these really gigantic 8 or 10 ohm resistors in the lab for high power, but we don't have them in your kit. So you have to do part 3.3 in Circuit Lab. But you do see that the Mosfet does a much better job than the bipolar transistor at putting essentially all of the useful power into the load, which sits up here, rather than wasting it in the transistor. Okay, so that's what you will see when you look in Circuit Lab. And I guess I wrote out some numbers where I found, like for the particular numbers we study, that the bipolar transistor wastes about 5 times as much power as the FET wastes. That the FET, kind of the ratio of wasted power to useful power for the FET is like about 0.5%, and the ratio of wasted power to useful power for the BJT is like 3% for the configuration you see in part 3.3, where we're trying to switch on and off like an 8 ohm an 8 ohm load. Okay. So I'm going to move on now to part 4 in the next video.